Metaskin facade. We don't just know facades, we define them. A dedicated platform for the art and science of building envelopes and architectural skins. With over 2 decades of hands-on experience, we bring you practical insights, technical expertise, and the latest innovations in facade design and execution. PKS Media Broadcasting Group. Metaskin facade. We don't just know facades, we define them. Chapter 2, Facade Thermodynamics. Facade Thermodynamics. Orientation is the engine of performance. Every facade begins with the sun. Orientation is not style, it is thermodynamics. It decides whether a building works with the climate or against it. In India's fierce light, each degree of alignment turns physics into performance, and the facade into a living instrument of energy and comfort. The facade engineer's first rule. In facade engineering, orientation is non-negotiable. It is the single most decisive factor that determines whether a building works with the climate or against it. Every facade behaves differently under the sun. How a surface receives, reflects, or resists solar radiation directly affects 3 measurable outcomes. Thermal load. The energy required for cooling or heating. Daylight autonomy. The quality and quantity of usable daylight. Material durability. How long finishes, sealants, and coatings survive under heat stress. In India, where the sun dominates most of the year, orientation becomes the heart of facade design. A facade that performs perfectly in Chennai may underperform in Gurugram if its orientation and solar geometry are ignored. The sun behaves differently in every latitude, the facade must adapt. Key message: the sun never negotiates. The facade must respond with thermodynamic intelligence. Understanding solar geometry in practice. To design a facade that truly responds to the sun, we must understand how the sun moves relative to our site. 3 angles govern this motion. Solar altitude, alpha. The height of the sun above the horizon. High altitude produces nearly vertical rays, summer noon. Low altitude shallow rays penetrating deeper indoors. Solar azimuth, gamma. The compass direction from which sunlight strikes a facade at a particular time, east, west, north, or south. Solar declination, delta. The Earth's seasonal tilt, varying from plus 23.45 degrees in June, summer solstice, to minus 23.45 degrees in December, winter solstice, as Earth revolves around the sun. Plotting these parameters on a sun path diagram allows us to visualize solar exposure at any hour of the year, converting facade design from aesthetics to predictive, data-driven thermodynamic engineering. How the sun's path shapes facade design. How the sun's path shapes facade design. Altitude, vertical height. Summer sun, yellow path, is high, needs horizontal shading, overhangs, on the south facade. Winter sun, red path, is low, allows passive heating through the same windows. Azimuth, horizontal direction. East and west facades receive low-angle sun for long hours. They demand vertical or dynamic shading, fins/louvers, to control glare and heat. Equinox effect. The sun rises due east and sets due west, exposing both facades equally, reinforcing the need for vertical shading design. In short, a well-oriented facade decides whether a building wears an eyelid, horizontal, or a mask, vertical. Solar impact on building envelopes. An orientation strategy. Each cardinal orientation dictates a unique thermal and luminous strategy for the facade under Indian climatic conditions. The sun's behavior is not uniform, it changes by direction, season, and altitude. Therefore, each facade must be designed with specific shading geometry, glazing type, and material response to handle its solar exposure effectively. Directional behavior of facades in Indian climatic conditions. Orientation. North. Solar exposure. Receives soft, diffused light throughout the year. Minimal direct solar radiation. Thermal strategy. Minimal heat gain, can use lighter materials and higher window wall ratio. Daylight and visual comfort strategy. Ideal for workspaces requiring uniform daylight. Maximize VLT glazing for daylight autonomy. Orientation. South. Solar exposure. Consistent high-angle sun, especially in summer. Thermal strategy. Use horizontal shading devices, overhangs, light shelves, to block high summer sun but permit winter gain. Daylight and visual comfort strategy. Balance daylight with low glare, maintain moderate glazing ratio and low E-glass. Orientation. East. Solar exposure. Low-angle morning sun, short duration but intense. Thermal strategy. Use vertical fins or deep reveals to reduce morning glare and solar ingress. Daylight and visual comfort strategy. Use spectrally selective solar control low EDGU with low SHGC and moderate VLT, plus vertical fins for low-angle morning sun. Orientation. West. Solar exposure. Exposed to prolonged low-angle afternoon sun, the harshest thermal load. Thermal strategy. Use vertical fins, double skin systems, or high-performance low-E glazing with fritting. Consider surface cores as thermal buffers. Daylight and visual comfort strategy. High risk of glare, prioritize visual comfort through dynamic shading or perforated screens. Orientation is the core of performance. In Indian projects, balancing the response of all four facades is non-negotiable. A design that ignores proper solar orientation will inevitably suffer from higher peak cooling loads, making the building entirely dependent on oversized, energy-intensive HVAC systems. Conversely, a facade that respects solar geometry begins to thermally buffer its interiors, moderating heat flow, reducing daily temperature swings, and maintaining comfort naturally. This strategic thermodynamic alignment directly leads to lower operational energy, reduced consumption through passive design, extended material lifespan, coating and finish durability, reduced carbon footprint, sustainable environmental impact. Ultimately, orientation transforms the facade from a passive shell into a climate-responsive, thermodynamic skin, the building's first line of environmental defense. Thermal behavior and energy balance. Quantifying performance. Solar radiation incident on any facade consists of three distinct components, each contributing to the building's internal thermal load. Direct radiation. Sunlight striking the surface along a straight path, governed by solar azimuth and altitude angles. Diffuse radiation. Scattered solar energy originating from the atmosphere, e.g., under cloudy or hazy sky conditions. Reflected radiation. Solar energy reflected from nearby surfaces such as the ground, water bodies, or adjacent buildings. When this combined energy reaches the building envelope, a portion is reflected, some is absorbed by the facade material, and the remainder is transmitted through the glazing. The absorbed fraction is converted into sensible heat, which significantly increases the internal cooling demand. Key building physics parameters. Parameter. U value, W/M superscript 2K. Technical description. Represents the rate of non-solar heat transfer, via conduction and convection, through the wall or glazing assembly. Performance goal. Lower equals better thermal insulation and reduced heat transfer. Parameter. SHGC, solar heat gain coefficient. Technical description. The fraction of incident solar radiation, both absorbed and transmitted, that enters the interior as heat. Performance goal. Lower equals better for cooling dominant climates to minimize unwanted solar gains. Parameter. Albedo. Technical description. Indicates a surface's ability to reflect solar radiation, ranging from 0, perfect absorption, to 1, perfect reflection. Performance goal. Higher equals better, as it reduces surface temperature and heat flux into the wall. Parameter. Thermal lag, time. Technical description. The time delay for heat absorbed on the exterior surface to propagate and re-radiate indoors. Performance goal. Higher equals better, offering improved thermal stability and lower peak HVAC loads. The value of orientation and energy load. Field measurements in composite Indian climates, such as Delhi, NCR, clearly demonstrate the thermal implications of orientation. 55 degrees Celsius. West facade. Without shading. 35 degrees Celsius. South facade. With shading. 20 degrees Celsius. Temperature differential. Impact on cooling load. This 20 degrees Celsius temperature differential directly translates to a substantial reduction in peak cooling load and also prolongs the lifespan of facade materials. Modern dynamic simulation tools, such as Design Builder, Climate Studio, and Energy Plus, quantify this by calculating incident solar radiation, WH/M superscript 2, and the resultant energy transfer for each orientation. However, even before resorting to advanced simulations, a sound understanding of solar geometry can guide nearly 70% of core facade design and optimization decisions, ensuring both thermal efficiency and architectural integrity from the outset. Daylight and solar control integration. Shaping the light. Daylight control represents the intersection where orientation and facade performance become visually perceptible. In high-performance facade design, the intent is not to exclude sunlight, but to shape and regulate it, redirecting soft, diffuse daylight deeper into occupied zones while suppressing glare and limiting unwanted solar heat gain. A well-designed shading system is calibrated precisely to the solar geometry of the site, responding to both azimuth and altitude angles throughout the day and across seasons. Elements such as horizontal overhangs, effective for south facades, vertical fins, ideal for east and west facades, and light shelves or reflective baffles, for daylight redirection, create a dynamic balance between daylight penetration and solar control. Key facade performance metrics. Parameter. VLT, visible light transmittance. Description. Percentage of visible light transmitted through glazing. Design goal/orientation response. Moderate range, 40 to 60%, ensures sufficient daylight with minimal glare, especially on east/west facades. Parameter. DF, daylight factor. Description. Ratio of indoor illuminance to available outdoor daylight under overcast conditions. Design goal/orientation response. 2 to 5%, ideal for balanced brightness, lower for perimeter glazing, higher for deeper zones. Parameter. UDI, useful daylight illuminance. Description. Percentage of time the space receives optimal daylight, 100 to 2000 lux. Design goal/orientation response. 70 to 80% UDI indicates well-distributed, glare-free daylight. Parameter. SC, shading coefficient. Description. Ratio of solar heat gain through glazing to that through clear glass. Design goal/orientation response. Less than or equal to 0.35 for east/west facades, provides effective solar control without darkening interiors. When calibrated effectively, such daylight-solar integration can reduce artificial lighting energy by 30 to 50%, enhance visual comfort, and lower peak cooling demand, a critical factor in cooling dominant Indian office environments where east and west glazing otherwise drive persistent operational challenges. In essence, orientation-responsive daylight design transforms facades from passive barriers into active environmental moderators, balancing light, heat, and visual comfort in measurable, performance-driven terms. Orientation-specific material strategy. The facade skin. In India's high UV and dust-laden climate, facade materials on sun-exposed orientations, particularly south and west, undergo accelerated aging, discoloration, and surface degradation. Hence, material selection must be treated as a performance strategy, not merely an aesthetic decision. The objective is to choose materials with optimal albedo, surface reflectivity, and thermal inertia, mass, to regulate surface temperature and control heat flux into the building envelope. High albedo materials reduce radiant heat absorption, while materials with high thermal mass delay the inward transmission of heat, improving indoor thermal stability. Material performance parameters. Parameter. Function. Ideal range/type. Design intent. Parameter. Albedo. Function. Reflects incident solar radiation. Ideal range/type. 0.40, 0.60, greater than or equal to 0.60 for west facades. Design intent. Keeps surface cooler and reduces UV stress. Parameter. Thermal inertia, kJ/M superscript 2K. Function. Stores and delays heat transfer. Ideal range/type. Medium, high, 100 to 200 kJ/m superscript 2K. Design intent. Shifts peak heat gain to evening hours. Parameter. Emissivity. Function. Re-radiates absorbed heat to surroundings. Ideal range/type. 0.80 to 0.95. Design intent. Aids nighttime cooling and stabilizes envelope temperature. Parameter. Surface finish. Function. Influences heat absorption and maintenance. Ideal range/type. Smooth, light-colored, low-porosity coating. Design intent. Minimizes dust accumulation and maintains reflectivity. Parameter. Durability index. Function. Resistance to UV, dust, and weathering. Ideal range/type. Greater than or equal to 7/10. Design intent. Extends facade lifespan on sun-exposed sides. The power of thermal mass. A standard 230 mm RCC wall can delay peak heat transfer by approximately 5 to 6 hours, shifting cooling load away from the afternoon peak and reducing HVAC demand. The power of thermal mass. On sun-facing facades, thermal mass walls, constructed using reinforced concrete, dense masonry, or stone, play a critical role in moderating heat flow through a phenomenon known as thermal lag. A standard 230 mm RCC wall can delay peak heat transfer by approximately 5 to 6 hours. This allows the wall to absorb solar heat during midday and release it gradually in the evening when ambient temperatures are lower. The result shifting cooling load away from the afternoon peak and reducing HVAC demand and maintaining a more stable interior temperature throughout the day. This orientation-specific use of material mass not only enhances thermal comfort but also extends the lifespan of facade finishes, reducing thermal fatigue and maintenance costs in the long term. South facades, light-colored finish plus moderate thermal mass. West facades, high reflectivity finish plus dense wall material. North facades, lightweight systems plus minimal shading required. East facades, moderate reflectivity plus easy clean coating. Climate-responsive dynamic facades. The facade is no longer a static architectural element, it has evolved into a dynamic, climate-adaptive interface. Advances in building technology now enable facades to respond intelligently to solar orientation, adjusting in real time to changing environmental conditions. Electrochromic glazing. Smart glass that automatically adjusts transparency based on solar intensity and daylight sensors. Motorized louvers. Automated shading panels that tilt and adjust to optimize daylight while minimizing glare. BIPV systems. Building integrated photovoltaics that generate renewable energy while providing solar control. For diverse Indian climates, the most effective approach lies in hybrid facade systems that combine passive strategies, correct orientation, natural ventilation, and fixed shading with active technologies, achieving the ideal balance of thermal comfort, daylight quality, and renewable energy efficiency. Case study, Mastering the Sun. Sector 47, Gurugram, 28.46 degrees north. The cost of direction, why orientation trumps all. In India's composite climate, orientation is not an aesthetic preference, it's a thermodynamic variable. For high-rise commercial developments, the decision made at the concept stage can redefine long-term energy performance. 22% savings. A simulation study of a 10-story commercial tower in Sector 47, Gurugram demonstrated that realigning the building's axis to the sun's path reduced annual cooling energy by approximately 22%, while improving daylight uniformity and occupant comfort. The study underscores a simple truth: buildings that align with the sun perform with the climate, not against it. Solar radiation is almost equal to 5.5 kilowatt-hours per square meter per day average. Temperature range: 5 to 45 degrees Celsius annual variation. Climate type: composite. Hot dry summers plus cold winters. The geometry challenge. Altitude versus azimuth. Gurugram's latitude, 28.46 degrees north, creates extreme seasonal shifts, dictating the two angles a facade must handle. Solar event. Max solar altitude, alpha. Sunrise azimuth. Design implication. Solar event. Summer solstice, June 21st. Max solar altitude, alpha. 84.7 degree, overhead. Sunrise azimuth. 61 degrees northeast. Design implication. Requires horizontal shading for eye sun. Solar event. Winter solstice, December 21st. Max solar altitude, alpha. 38.1 degree, low. Sunrise azimuth. 116 degrees southeast. Design implication. Requires vertical shading for low-angle glare. Interpretation. At Eurogramm's latitude, the facade must manage both high-altitude overhead sun in summer and low-angle glare in winter, necessitating dual shading geometries. Solar geometry. Altitude, alpha. Defines the sun's vertical position above the horizon. High in summer, low in winter. Azimuth, gamma. Defines the sun's horizontal direction, east-west movement. Critical for facade shading geometry. Heat gain, Q equals A times SHGC times I. Whereas total solar irradiance, defined by solar altitude alpha and azimuth gamma. Orientation. The 4 times load, quantifying orientation risk. Each facade orientation receives a distinct level of solar exposure, directly influencing its cooling energy demand. Simulation results reveal a striking disparity. West-facing facades experience nearly 4 times more solar load than north-facing ones. This imbalance is not aesthetic, it is thermodynamic. Such variance must govern the form, glazing ratio, and material selection of every facade, ensuring that design intelligence precedes mechanical dependence. Orientation. Average incident solar radiation, I peak. Relative load factor. Key design focus. Orientation. North. Average incident solar radiation, I peak. 240W/m superscript 2. Relative load factor. 1.0, baseline. Key design focus. Maximize glazing for diffuse daylight, minimal shading required. Orientation. South. Average incident solar radiation, I peak. 620W/m superscript 2. Relative load factor. 2.6, controllable. Key design focus. Horizontal overhangs or light shelves to block high-altitude summer. Sun and allow winter penetration. Orientation. West. Average incident solar radiation, I peak. 960W/m superscript 2. Relative load factor. 4.0, worst case. Key design focus. Deep vertical fins, dual skin facade, or high thermal mass materials. To buffer afternoon heat gain. The form decision, north, south versus east, west. The simplest yet most consequential orientation question: which direction should the building's long axis face? Option 1, optimized. Long axis, east, west. Major facades, north and south. Annual cooling load, 154 kilowatt-hours per square meter. 22% saving. Option 2, unoptimized. Long axis, north-south. Major facades, east and west. Annual cooling load, 198 kilowatt-hours per square meter. Higher load. By simply aligning the long axis east-west, the design reduces exposure of the thermally critical east and west facades. This adjustment achieves a 22% reduction in annual cooling energy, improves daylight uniformity, and stabilizes interior comfort. It's a one-time decision at the concept stage, yet it defines the building's energy performance for the next 50 years, proving that orientation is the first act of thermodynamic intelligence in facade design. The glazing calculation, orientation-specific SHGC. To quantify the effect of solar geometry on facade performance, let's compare 2 facades under an unoptimized orientation, east-west axis, using the same glazing parameters. Glazing ratio, GR 45%. Solar heat gain coefficient, SHGC 0.25. Facade orientation. Condition. Peak solar heat gain, QS. Observation. Facade orientation. South facade. Condition: high solar altitude, controllable through horizontal shading. Peak solar heat gain, QS, 27.9 kilowatts. Observation: manageable thermal load. Facade orientation: west facade. Condition: low solar altitude, intense afternoon radiation, difficult to shade. Peak solar heat gain, QS, 43.2 kilowatts. Observation: harsh, sustained heat gain. South facade, controllable. It equals 620 W/m superscript 2. Solar is equal to 0.45 by 400 square meters times 620 W/m superscript 2 times 0.25 is equal to 27.9 kW. West facade, harsh. It equals 960 W/m superscript 2. Solar is equal to 0.45 by 400 square meters times 960 W/m superscript 2 times 0.25 is equal to 43.2 kW. Impact: even with identical glazing specifications, orientation alone increases the solar load on the west facade by approximately 55%. This variance highlights why each facade orientation demands distinct glass properties and shading geometries. A single SHGC value cannot serve every direction in a thermodynamically optimized envelope. Designing the shade geometry is key. Shading must be designed based on the sun's angle for that specific facade. Effective shading design begins with understanding the solar geometry specific to each facade. The shading depth and orientation must respond to the sun's altitude and azimuth angles, ensuring that the facade filters, not fights, the sun. South facade, altitude control. For south-facing facades, the challenge is to block the high summer sun while allowing winter sunlight to penetrate indoors for passive heating. Using trigonometric analysis for a window height, h equals 1.5 m, the optimal horizontal projection, P, is determined by the solar altitude angle, alpha. Tan alpha equals h/p. At Gurogram's latitude, 28.46 degrees north. Summer solstice altitude is almost equal to 84.7 degrees. Winter solstice altitude is almost equal to 38.1 degrees. Results: an overhang projection of approximately 1.9 m effectively blocks the high summer sun while permitting the lower winter rays, achieving seasonal shading balance. The theoretical 1.9 m projection represents the maximum shading depth that would fully block even the low winter sun. In practice, designers adopt a reduced projection, is almost equal to 1.0 to 1.5 m, to balance summer shading with limited winter sun admission for passive comfort. Design guideline: vertical fins spaced at roughly 1.2 times window width efficiently intercept the oblique morning and afternoon sun, minimizing side glare and solar penetration. Key takeaway: shading geometry is direction specific. Horizontal devices belong to altitude-driven facades, south, while vertical fins govern azimuth-driven facades, east/west. When geometry follows the sun, the facade achieves both visual comfort and thermal stability through design, not mechanical compensation. Comfort and cost, the final impact. Orientation is not an abstract design choice, it translates directly into thermal comfort, visual quality, and operational cost. Orientation: north. Peak summer surface temp, degree C, 33 degrees Celsius. Interior temp, degree C, 27.9 kilowatts. Observation: receives soft, diffuse radiation surface temperature. Remains close to ambient, ensuring thermal stability. Orientation: west. Peak summer surface temp, degree C, 48 degrees Celsius. Interior temp, degree C, 43.2 kilowatts. Observation: prolonged low-angle afternoon sun causes extreme solar loading, internal air temperature rises by is almost equal to 6 degrees Celsius even without conditioning. Thermal comfort: west-facing interiors record temperatures up to 6 degrees Celsius higher solely due to solar exposure, placing a disproportionate load on the HVAC system. Daylighting: north-facing glazing achieves an optimal daylight factor, dF, of 2.8 to 3.2%, delivering uniform, glare-free illumination, unlike the high-contrast glare typical of West facades. Financial outcome, orientation optimization only. 22%. Energy reduction. From 198 kilowatt-hours per square meter 154 kilowatt-hours per square meter. Indian rupee 21.1 L. Annual energy savings. Assuming 6,000 square meters facade area. And 8 Indian rupees/kilowatt-hour tariff. Orientation is the building's first dialogue with the sun. Each degree of alignment reshapes its energy, comfort, and lifespan. When form follows the sun, performance follows effortlessly. Orientation isn't geometry. It's the first act of sustainability. In the next episode, the facade turns from the sun to the wind, where thermodynamics meets aerodynamics.